Bismillahirrahmanirrahim. Dear students, let's solve first problem of this week. Problem number 1, and this problem is related to an overhanging beam. Let's draw the beam. We have a hinge support here and a roller support at this point, and we have a point moment acting here. Point moment is in clockwise direction and its magnitude is 20 kilonewton meter, and there is a point load as well. Load is acting in downward direction with a magnitude of 8 kilonewton, and we have a UDL acting on the overhang. Intensity of the UDL is 15 kilonewton per meter. These points are A, B, and reaction here, and there will be one vertical reaction here, and these distances are 2 meter, 1 meter, 2 meter, and 3 meter. So this is the given problem, and in this problem we have how to deal with overhanging part and how to deal with point movements. Immediate point on the span. The solution, and we know that first step of solving this beam is to determine the reactions of the beam, and for that we will apply the conditions of equilibrium. So let's convention is that we will take upward forces as positive. Now how many? Let's call this reaction as RA and this reaction as RB. So there are two forces acting in upward direction, RA and RB. So RA plus RB, and then we have this 8 kilonewton force acting in the downward direction, so minus 8, and then this UDL is acting in downward direction. This is basically rectangular load, and I told you before that this is another way of showing rectangular load. Normally in our manual calculation we use this symbol. So how much is the magnitude of the load? 15 kilonewton per meter is the intensity, and 3 meter is the span on which it is acting. So 15 into 3, and as it is acting in downward direction, so this is negative. And what about this movement? This movement will not come in this equation because we are we are applying sigma Fy equal to 0, and we are applying it on the forces, not on the moments, and this should be equal to 0. If we rearrange this equation, we get RA plus RB equal to 53, and in this equation we have two unknowns, so we cannot solve this equation. Let's move ahead and apply the other condition of equilibrium. The second condition, we may take sum of moment about point B equal to 0, and our convention is clockwise movement as positive. Okay, so let's start from this end. RA is producing clockwise movement about point B, so RA, the movement will be positive. RA into how much is the lever arm? It is 5, and then we have this movement. As we are applying sum of moments about point B equal to 0, so this movement will appear in the equation, and movement is in which direction? It is in clockwise direction, so it should be positive 20, and as it is a movement by itself, so we do not need to multiply it with any lever arm. And then we have this force 8 kilonewton. this force is producing movement in counterclockwise direction about point B. So we'll say minus 8 into 2. 2 is the lever arm, and then we have this force RB. The reaction RB is passing through point B, so it will produce zero movement about point B. It will not appear in the equation. And then we have this UDL. 15 into 3 will be the magnitude of the UDL, and then we'll see the lever arm. But first, what is the direction of movement? It is in clockwise direction about point B. So we should take it as positive. 15 into 3 is the magnitude of the resultant, and 3 by 2 is the lever arm, because the resultant will be acting at the center, something like this. This is the resultant, and it will be 15 into 3. And what else? Do we have any other force producing movement about point B? I think not. So let's put it equal to 0. Now if we calculate the value of RA, because in this equation we have only one unknown, so we can calculate it. RA comes out to be minus 14.3 kilonewton. This is the first time when our reaction has come out to be negative. Now what does it mean? Negative reaction means that the assumed direction of reaction is incorrect. We assumed RA to be in upward direction, but negative sign means that that upward direction is incorrect. So we can say that the assumed direction of RA is wrong. So it means in reality RA is acting in upward direction. So when we will make further calculations, we will incorporate that. But using this RA, we can calculate the value of RB by plugging in RA into equation number 1. So equation number 1 employs RA. Equation number 1 implies that RA minus 14.3 plus RB equal to 53. This implies RB equal to 67.3 kilonewton. So in this way we have got both the reactions, RA as well as RB. Now next step is to divide the beam into portions, and for that our rule is that wherever we see any change in applied loading, whether in terms of a force or in terms of movement, and we see any change in support condition, we consider those points as the dividing points between different portions. So we start from here, point A, and as we move in the rightward direction, at this point we see a change in the applied loading. Here no load was present, and at this point we have a point movement. So we can call this point, if we already have A and B on the beam, so we can call this point as point C. So AC is one portion, and then if we move further from C, we come to this point where we have a point load. So this point should be another dividing line. We'll call this point as D, and then we have a support here at point B, so definitely it will be one portion, like DB will be one portion. And then we have this overhang. In overhang we have a UDL. I have marked the resultant, but resultant will not divide this part into different portions, because you see I have marked resultant with a dashed line, because this is not a real point load acting at this point. So this entire overhang can be considered as one portion, and we will say this point as point E. So if I enlist the portions AC, portions will be AC, CD, DB and BE. So in this case we will have 4 portions. So we'll divide this beam into 4 portions. Okay, let me see, is there any problem with light? Oh, Okay, so we have divided the beam into portions. Now we will consider all these portions one by one, and we will draw the free body diagram of each portion and write down the equation of shear and bending moment. So let's proceed. Let's consider portion AC first. Portion AC. And for portion AC, now if I mark the sections on the main beam, one section will be considered here, one in CD part, one in DB part, and the fourth one will be considered here. Now whether I mark the section here or on the other side of the resultant, it does not matter. This section, when we will write down equation for this, that equation will be valid for the entire portion BE. Okay, so now let's come to portion AC. In this portion we have a hinge support at point A. Here is the section. Reaction, as we have already seen that RA, initially we assumed it to be in upward direction, but the answer came out to be negative. It means that is incorrect. So for all our further calculations, we will consider RA in the downward direction. Here is RA, 14.3 kilonewton, and we have this X, variable X, running in this direction up to the section, and at the section we have exposed forces V and M, and according to our convention we always take shear in downward direction and movement in counterclockwise direction. Okay, so I think this completes the free body diagram for this portion. Now let's write down the equations for shear and bending moment, and we also need to write down the range of X is from 0 to 2 meters. Let's apply the conditions of equilibrium. Sigma Fy equal to 0, and our convention will be upward forces will be taken as positive. How many vertical forces are there? This 14.3 kilonewton, it's in downward direction, so minus 14.3, and then this V also acting in downward direction, and that's it, that's equal to 0. So this implies V is equal to minus 14.3 kilonewton, and in this equation there is no variable X, so it means that the entire value, the magnitude of shear is constant for the entire length of this portion AC. So we have shear here. Next we will write down the equation for bending moment, and we always write down the equation of bending moment about the section. We take sigma mx equal to 0. Convention is clockwise will be taken as positive. Now this 14.3 kilonewton will produce movement about the section in counterclockwise direction, so it will be taken as negative, minus 14.3, and lever arm is X. What else? Then we have this moment M in counterclockwise direction, so minus M, and that should be equal to 0. If I rearrange this, I get M is equal to minus 14.3 X. Now in this equation we have variable X. It means that the value of bending moment is not constant throughout the length of this portion, so we need to calculate the value for point A as well as for point C. So at point A, how much is X? X is equal to 0 at point A, so MA will come out to be minus 14.3 into 0, and that is equal to 0. And is this 0 logical? We have a hinge support at point A and there is no externally applied moment at A, so this 0 is totally logical. This is a hinge support. So this is totally fine. Next we have point C. So at point C, X is equal to how much? X is equal to 2 meters. So MC will be equal to minus 14.3 into 2, and that is minus 28.6 kilonewton meter. So this is the value of moment for point C. This completes our calculation for portion AC. Now let's move to the next portion, portion CD. What is the range of X? X varies from 2 to 3 meters for this portion. Now let's draw the free body diagram. Hinge support at A, reaction acting in the downward direction. This is a section at distance X. We have a point movement here acting in clockwise direction. Magnitude is 20 kilonewton meter. Shear force V acting in downward direction and M in counterclockwise direction. Magnitude of the reaction is 14.3 kilonewton. This point is C according to our nomenclature. So here we have drawn the free body diagram of portion CD. Now let's apply sigma Fy equal to 0 and sigma Mx equal to 0. So sigma Fy equal to 0 with upward forces taken as positive. How many vertical forces are there? We have minus 14.3 and minus V, and that is equal to 0. There is no other vertical force. So V comes out to be minus 14.3 kilonewton. Again, for portion CD, the value of shear is constant. It's minus 14.3 kilonewton. Now let's apply sigma Mx equal to 0 with clockwise as positive. Okay, this force will produce counterclockwise movement about the section, so it will be minus 14.3 into X. X is the lever arm, and then we have this movement in clockwise direction. It should be positive 20 kilonewton meter, and then this movement in counterclockwise direction, so it will be taken as negative M, and that is equal to 0. If we rearrange this equation, we get M is equal to 20 minus 14.3 X. So in this equation we have variable X. It means the value of movement will vary from point C to point D. So we will consider it for both the points. We will calculate it. At point C, at C, X is equal to 2 meters. So MC is equal to 20 minus 14.3 into 2, and that comes out to be minus 8.6 kilonewton meter. And at D, X is equal to 3 meters and MD will be equal to 20 minus 14.3 into 3, and it comes out to be minus 22.9 kilonewton meter. Right? So this is the value of moment at D. This is at D and this is at C. Now one observation here is that the value of bending moment at point C is different from portion AC side as compared to the CD side, and we have discussed this point earlier, that whenever we have a point movement acting at any point, then the value of bending moment will be different on both the sides, and that difference is actually equal to the difference of to the magnitude of the point movement acting. So see, it's 28.6 here and it minus 8.6 here. So how much is the difference? The difference is exactly equal to 20 kilonewton meter, and 20 kilonewton meter is the moment acting at this point C. Okay, so with this we have completed 2 portions. Now let's move to the third portion. Third portion is portion DB. Portion DB, value of x ranges from 3 to 5 meters for portion DB. Now let's draw free body diagram. We have a hinge support here, a reaction acting in the downward direction with a magnitude of 14.3 kilonewton, and we have a point movement in clockwise direction 20 kilonewton meter, and then we have a force acting in downward direction of magnitude 8 kilonewton. This is A, C, and this is D. Here is our section. Shear V acting in downward direction, moment M in counterclockwise direction. X varies from support A up to the section, and the limits are 3 to 5 meters. Now what else do we need? I think this free body diagram is complete now. Let's apply the conditions of equilibrium. Let's apply sigma Fy equal to 0 first, and our convention will be we will take upward forces as positive. Okay, so let's apply. Minus 14.3 kilonewton is acting in downward direction, then minus 8 kilonewton is also acting in downward direction, and then we have shear V also acting in downward direction. So that's equal to 0, and this implies V is equal to minus 22.3 kilonewton. And again, the value of shear is constant for this region, so we don't need to calculate the value of shear for separately for points D and B. Now for bending moment, sigma mx equal to 0, clockwise movement as positive. Starting from this point, 14.3 kilonewton is producing movement in counterclockwise direction. So minus 14.3 into x, then we have this movement in clockwise direction, so it will be positive 20 kilonewton meter, and then this 8 kilonewton force producing a movement in counterclockwise direction. How much is the lever arm for this force? This distance is 2 meters, this distance is 1 meters. So from A to C it's 2 meter, and from C to D is 1 meters. It means that the distance between A to D is 3 meters, and distance between A to the section is x. So how much will be this distance? Because we want this distance, this is the perpendicular distance between this 8 kilonewton load and the section, and this should be equal to x minus 3, right? We are calculating movement about the section, so we need perpendicular distance between 8 kilonewton and the section, and it is x minus 3. So 14.3x with a negative sign plus 20 minus this 8 into x minus 3, and then this minus m equal to 0. Now if we rearrange this equation, m is equal to minus 14.3x plus 20 minus 8x plus 24, and finally m comes out to be 44 minus 22.3x. So this is the equation of movement for portion DB. Now let's plug in the value of x for point D and point B. At D, x is equal to 3 meters, so MD is equal to 44 minus 22.3 into 3, and this comes out to be minus 22.9 kilonewton meter. This is the value of moment at point D. and at B x is equal to 5 meter. So MB comes out to be 44 minus 22.3 into 5, and the answer is minus 67.5 kilonewton meter. In this way, we have got the value of bending moment for point D as well as point B, and an observation at this point is that at point D the value of moment is minus 22.9, and what about the previous value that came from portion CD, that was also equal to minus 22.9 kilonewton meter. So that verifies our idea that we described earlier, that for any point when there is no point movement, the value of bending moment remains same from both the sides. Okay, so this completes calculation for portion DB. Now the last portion BE. X ranges from 5 to 8 meters. Let's draw the free body diagram. We have a hinge support, point movement 20 kilonewton meter, and then we have a point load, magnitude is 8 kilonewton, and then we have a roller support here, and under the roller support we have a reaction. Similarly, we have a reaction under the hinge support, 14.3 kilonewton and 67.3 kilonewton. We have a UDL in this part. Here is the section. Intensity of the UDL is 15 kilonewton per meter. This is distance is 2 meter, 1 meter. This is 2 meters. What else? The X will vary like this, and then okay, we'll identify the portion of the UDL when we'll be calculating the shear and moment. Okay, so this completes the bending moment free body diagram. Is there any other thing? Oh yes, I think the shear V and moment M are left. Okay, so now let's apply the conditions of equilibrium. Sigma Fy equal to 0 with sign convention, upward forces as positive. So starting from this side, 14.3 kilonewton is acting in downward direction, 14.3 kilonewton minus this 8 kilonewton plus 67.3, and then this minus this UDL. Now how much will be the magnitude of the UDL? The distance between point A and X, point A and the section is X. How much is this distance up to the starting point of the UDL? It is 2 plus 1 plus 2, 5. This much is 5 and this much is X. So what about this distance? This much will be X minus 5. Here we are, X minus 5. So this UDL is acting over a length of X minus 5. So we will, we'll write it down, minus 15 into X minus 5, and then minus V equal to 0. This completes the equation for shear. If we rearrange this, we get V is equal to 120 minus 15x. Now in this equation we have variable x. It means shear will vary along the length of the portion. So we'll have to calculate this shear separately for both the points. Point B, x is equal to 5 meters. So VB will be equal to 120 minus 5 into 5, and that is equal to 45 kilonewton. And at E, X is equal to 8 meters, and VE will be equal to 120 minus 5 into 8, and that is equal to 0. Is this 0 logical? What do we have at free end? At point E, we have a free end, and we have discussed that if there is no externally applied movement at point E, then the value of bending moment will be 0 at free end, and that is what we have in this situation. There is no externally applied movement and it's a free end, so the 0 value of bending moment at this point is totally correct. Okay, so now let's write down the equation for, oh sorry, this was not bending moment, this was shear. So also this is also true for shear. If there is no externally applied load at the free end, then the value of shear at the free end is also equal to 0. Okay, now let's move towards bending moment. Sigma mx equal to 0. How much is the value of x for this region? X varies for, oh we have already written, x for this region varies from 5 to 8, so we need to write down our convention clockwise as positive. Now let's write down the equation. 14.3, this is the section, it will produce counterclockwise movement, so it is minus 14.3 into x. Then this 20 is in clockwise direction, so it will be taken as positive 20, and then this 8 kilonewton force, it will produce counterclockwise movement, so minus 8 into, now how much is the lever arm, how much is the distance between this force and the section? Total distance from point A up to the section is x, and the distance between A and the force is 3, so this distance is x minus 3. And then we have this reaction, it will produce clockwise movement, so positive 67.3, and how much is this distance, 67.3 into this distance is x minus 5. Now what else is left? This UDL. For moment calculation, we will have to consider the resultant of the UDL. The resultant of the UDL will act here at the center, and how much will be this distance? This total distance is x minus 5, and this is the center point of this distance, so this will be x minus 5 divided by 2. Okay, so this resultant will produce moment in counterclockwise direction, so it will be taken as minus 15 into x minus 5 is the magnitude of the resultant. 15 is the vertical dimension and x minus 5 is the horizontal dimension of the rectangular load, and then the lever arm is x minus 5 divided by 2 minus m. This minus m is this m, and that is equal to 0. So this completes the equation of bending moment for this part. Now it is your choice. If you want to simplify the equation, you can do that, or you can simply plug in the value of x and get the answers for bending moment at point B and point E. So I think I will not simplify this, because that will involve more calculations, and I think we can avoid that. At B, x is equal to 5 meters. So all the terms in which we have x minus 5 will become 0 when we'll put x equal to 5. So minus 14.3 into x, x is 5, plus 20 minus 8 into 5 minus 3. The rest of the terms will become 0. Okay, and this will be equal to mb. So mb comes out to be minus 67.5 kilonewton meter. This is mb, and this mb is exactly equal to the mb value from the previous portion db, as there is no point movement acting at point b, so this is correct. Okay, last is at point E, x is equal to 8 meters, and in this case none of the terms will become 0, so we'll have to plug in the value of x in all the terms. Plus 20 minus 8 into 8 minus 3 plus 67.3 into 8 minus 5 minus 15 into 8 minus 5, and this is 8 minus 5 square divided by 2, right? And we have then mb, and this is equal to mb. So if we calculate it, we get mb equal to what? If you solve all these terms, you will get mb equal to 0, and this is totally logical because it's a free end and we do not have any applied moment at this point, so mb equal to 0 is totally fine. This completes our calculations about shear force and bending moment for all the 4 segments. Now let us draw shear force diagram and bending moment diagram. Okay, to draw shear force diagram and bending moment diagram, we will draw the beam again. Here is the beam. (20 kilonewton meter). We have this force acting in downward direction. This is 8 kilonewton, and then we have a roller support here, and we have a UDL here. Okay, UDL is 15 kilonewton per meter. This point is A, B, C, D and E. The reactions, we have a reaction acting in downward direction, 14.3 kilonewton and 67.3 kilonewton. What else? Do we have any other thing? I think no, I think that's complete. So now let's draw the guidelines to draw shear force diagram and bending moment diagram. Okay, now let's draw the 0, 0 line for shear force diagram. This is 0, 0 line. We are drawing SFD and our units are kilonewton. Our units are kilonewton. Okay, so how much is the value of shear for portion AB? Let's go back to our calculations. For portion AB, the value of shear, this is AC, the value of shear is constant and it is minus 14.3 kilonewton. For portion AC, This is 14.3 and it is on the negative side of 0, on the downward side of 0. And what is the value of shear for portion CD? It is again 14.3. There is no change, so we'll just continue with the same straight line. And what about the value of shear at point D? One value of shear is 14.3 and that came from portion CD. The other value is 22.3, minus 22.3. So we'll move in the downward direction, minus 22.3. And then for this portion, it remains constant. It's the same point, minus 22.3. And then at point B, from portion BE, the value of shear is 45. So we will move in the upward direction. It is 45 here. And then for point E, the value of shear is 0. We have a UDL here. We have 45 kilonewton here, and the value of shear is 0 at this point. So with what degree line we should join these 2 points? For that we will have to look at the degree of the equation for portion BE. If we look at the equation of shear for portion BE, this is the equation for portion BE, and this is a first degree line, first degree equation. It means that we should join portion points B and E with a straight line, with a linear line. So let me draw a linear line. Here we go. So we have a first degree line here. This part of the shear force diagram is negative and this part is positive. This is SFD. Now let's draw bending moment diagram. 0, 0. We are drawing BMD and the units are kilonewton meter. The value of moment at point A is 0. The value of moment at point C, first value is 28.6. And if we look at the equation of bending moment for portion AC, this is the equation of bending moment for portion AC. It is minus 14.3 x. The value, the power of x is 1, the degree is 1. So we will join these 2 points with a straight line, like this. And then what is the other value of moment at this point? The other value of moment is 8.6. That came from the next section and it's also negative. So we have 28.6 and then we have 8.6. And then for this point, point D, how much is the value of bending moment? If we look at our calculations, the value is 22.9 with a negative sign. So, and again the equation is linear, the first degree equation. So we'll join these 2 points with a straight line, 22.9. And then what is the value of bending moment at point B? It is minus 67.5. And the value, the degree of line, if you look at the equation, the degree of equation is 1. So we'll join these 2 points with a straight line, 67.5. And then for portion BE, at point B, value of moment is minus 67.5 and the value of moment at point E is 0. Now the question is that what should be the degree of the line? If you look at the equation for bending moment of portion BE, that is a second degree equation. So we will join these 2 points with a second degree line. And how these 2 points will be joined? What about the slope? Whether the slope will be increasing or decreasing? As the magnitude of shear force is decreasing, so the slope of bending moment diagram should also be decreasing. And regarding the slope query, actually I was getting a lot of questions about the slope, so I have made a small video of FAQ in our week 4 folder. So if you are not clear about the slope concept, you can see that small video clip that is in our week 4 folder. So as the magnitude is decreasing, we will draw a line with decreasing slope. If you look at the slope of tangent at this point, that is larger, and slope of tangent at this point is almost 0. This completes the bending moment diagram, and in this case the entire bending moment diagram is negative. Okay, now the last step. The last step is to draw the elastic curve, and in this case the entire bending moment diagram is negative. It means that the entire beam is hogging. So our entire elastic curve will be hogging, and elastic curve, just keep one thing in mind, it always passes through the supports. So here is the elastic curve. The entire bending moment diagram is negative. That is why the entire elastic curve is hogging. It is hogging up, and in this part the hogging will continue till it reaches the extreme end. This is definitely on a much exaggerated scale. The actual beam will not be deflecting by this much magnitude. This is just a tentative shape on a much exaggerated scale. Okay, so this completes our problem. With this, we'll just stop our recording here. Thank you very much.